So another IB circular motion example. We've got two objects which are moving. This point P is moving up and down in a simple harmonic motion. We've got point Q, which is in a circle, vertical circle, could be a Ferris wheel, moving at with a uniform speed. This first one could be a spring, a massed spring system, moving up and down. And this could be a Ferris wheel. Well, both of them have the same period t. So the time that it takes either for a full turn here or p to go completely down and back up is time capital T. When p is at the top of its motion and q is at its bottom, so it's just like what we're looking at here, it's one of the snapshots, let's say, of the system. So what's going to happen here, just after time is passing, this point will start going down with an acceleration downwards, and then it will go through some resting position, and then it will start to experience an acceleration up to a half of its motion when the acceleration is all up, and then it stops, goes back up again, and then it reaches its initial position again, goes through the resting position, experiences the acceleration, starts increasing up to when it stops at the same point where it began. Here in the circular motion, we've got the same thing happening. So when it gets up to this point is exactly when P has got down to that point, and then it completes a full turn. Well, since the question is only asking us for in which interval between successive times when the acceleration of P is equal and opposite to the acceleration of Q. So we're looking for moments in which one, for example, will be pointing down and the other will be pointing up, or vice versa, right? So equal and opposite. Well, the first thing that we may observe is that in the circular motion, the acceleration will always be pointing towards the center of our motion. So in any moment between those two situations here, when point Q is at the bottom and point Q is at the top, in any point, any other point that we choose, the acceleration would not be pointing upwards or downwards. In this motion here, this simple harmonic motion, the acceleration will always be pointing either up or down. It's a one-dimensional problem. Here, the acceleration sometimes will be pointing to the sides. For example, when it's going here, it's pointing perfectly to the right. When it's going down here, it should point perfectly to the left. That's because of circular motion. That's what's actually causing this vector, which is perpendicular to this acceleration, to change, and it will always be tangent to the motion itself, right? So if we analyze, when in the first situation, the first snapshot that we have here, the acceleration of point P is pointing down and acceleration of point Q is pointing up. So that would be one of the moments in which the accelerations are exactly equal and opposite. And then while this point is going up, the only other point that we have to check really is here. And when this point Q is all the way to the top, its acceleration will be pointing down. What's going to happen with point P? Well, P has, let's say, if this is a spring on a mass on a spring, the spring would be completely stretched, and we would be expecting some force upwards, some acceleration upwards. Our object has just stopped, so P would be at this point here in the bottom. So there would be a full acceleration up. And that would be another moment where both forces or accelerations are equal and opposite. Right? So if we compare those situations, how much time has elapsed from one to the other one? So in the first scenario up to the second scenario, half of the motion has passed, right? We would have to wait for two of those situations to happen, right? We will need another step here to get back to our initial configuration. So only half of the period's passing, it's half of the motion, so it's half of the time. Therefore, letter B.